Thank you, Matt. So what I really want to do in the next 15 minutes is basically walk you through some of the work that we are doing in the Kings River Experimental Watershed in the southern Sierra Nevada. And I would also like to show you some of the data that we have been collecting and what we are learning from that experiment. So the reason we are focused on the forested landscape is because this is overly used graphics that you may have seen so many times, that most of our water comes from the forested landscape. Especially in California, we have 45% of the total fresh water come from the national forest alone. And if you add that the private forest and private lands, the number goes up to 60%. We also know that the forest provide not just water, but they also sequester a lot of carbon. And here is a recent data that shows that the world forest, they absorb as much as 30% of the annual global CO2 emission. But this, the water from the forest as well as the carbon sequestration, that comes at a cost. And this is, graphics that I just did a back of, the calculation to just look at how much water forests are using across the continental U.S. And as you can see that the forest alone use about 1,100 millimeter a cubic kilometer per year. And to put that number in perspective, the Mississippi River, that average annual flow is 530 cubic kilometer per year. So that's about 2 times more water the forests are using than what getting out of the Mississippi River. Okay, so that's a lot of water. And most of that water that the forests are using, they're using in the form of transpiration. It's the water that the trees use when they do the photosynthesis. And given the forest, they need a lot of water. When that water is not available, forests, they become susceptible to so many different stresses, right? I mean, you get the forest dieback, you get the forest fire, mortality and things like that. And the forests, they go through all these changes over time. And what you see, I try to kind of conceptualize this in terms of this, really complicated diagram. And forgive me. So, the forests, they grow back, they grow under a given climate and conditions. If they find right amount of moisture, energy, they will grow. And as they grow faster, they require more water, right? And when the water is no longer available, they go through this disturbance regime. And the forests, they go through this cycle over and over. And at some, time scale, you'll find that the forests are under some sort of dynamic equilibrium, right? But that dynamic equilibrium, whether it's a 10-year, 100-year, or 150-year, they go through that cycle over and over again. But that dynamic equilibrium is under some sort of stable, climatic and management conditions, right, or natural, regime. But that natural regime is no longer there, and in part because of, we are seeing the climate change, the temperature is going up. We also, this is the recent graphics that shows that the snowpack in the Sierra Nevada is the lowest in the 500 years. Okay, so that's just this graphic shows what just the temperature can do for the Sierra Nevada. And there is another data set that shows that the forests are no longer the same, what used to be. And what you're seeing on these graphics here, that the number of tree density in 1911 versus in 2005 and 2007. So nearly 5 times more trees you have, and you have more carbon. You have more live tree carbon in the forest. So that basically what it means is you have more fuel, more biomass in the forest. We also see that the snowpack, whether you have the snowpack or you don't have the snowpack, is directly connected to the fire severity and the frequency. So given all these the changes in the climate and in the forest ecosystem, that natural equilibrium is no longer there. Okay, and now the question that we are trying to address is basically, can we restore the forest to some sort of a natural equilibrium state where the forest grow, and then they will be subjected to some disturbance regime, and then they will recover back over time. Okay, so that's what we are trying to do. And the goal of some of the there's a long list of goals that we have, because it's not just the forest that we are trying to, like restore, but there's a whole, a number of things that goes with it. And so I'm only highlighting some of them. So basically what we are basically trying to do is just understand the processes that control in terms of hydrology, as well as other, like aquatic ecosystem and forest ecosystem and things like that. And then try to, do some sort of treatment, some sort of restoration, activity in the forest, and see, how that affects those ecosystem services. And then if you can build a model that, allow us to predict and extrapolate those findings across, broader scale. So we have two set of watersheds in the southern Sierra Nevada. So this is, called the Providence Creek watershed. So we have 5 watersheds right there, and then we have 5 watersheds slightly higher elevation. It's called Bull watersheds. And this is, kind of messy table, but just shows that the elevation and area. So let's just focus on the elevation. So we are going from over 1,800 to 2,300 meter in elevation. Okay. So about 500 meter elevation gain. A lot of, most of the data that we started collecting in 2002, and some of those watersheds were treated in 2012 and 13 in the form of, selective thinning and also the, the controlled burn. But I won't be talking about those today. So I'm just going to focus more on, like, some of the data that we have collected before treatment and see what we can learn from them. And here's a laundry list of what the kind of data that we are collecting. We're collecting hydrologic data, stream flow, soil moisture, and things like that, and air quality data, sediment and turbidity, soils. We're doing some soil sampling and geomorphic analysis. We're also doing water chemistry analysis. And then in terms of biology, doing some sampling as well. So here's some of the data that we collected over the years, starting in 2004 to all the way to 2014. We just finished the 2015 water year data, but I don't have that in the graphics yet. And what I'm showing here is the precipitation variability across the 4 stations that we have. And what you see here is the precipitation only varies in the time, but not in the space. Across all 4 sites, despite you're going from 1,700 meter elevation to 2,400 meter elevation, there is no much difference in terms of precipitation throughout the year. And what it means, basically, there is no orographic effect at this elevation band in the southern Sierra. In terms of temperature, we are going from lowest elevation, slightly less than 3 degrees Celsius on average, to just below freezing point at the highest elevation. So you can, like just about 4 degrees Celsius difference from lowest elevation to highest elevation. And what this 4 degrees Celsius temperature difference does is, it creates a big difference in terms of the snowpack. So even though you have the same amount of precipitation, the high elevation site accumulates much more snowpack than the lowest elevation site, okay? If you calculate that, like how much precipitation falls as a snowpack, you're going from slightly over 30% to the lowest elevation site to over 50% at the highest elevation. So that's about 25% more precipitation falling as snow than rain, just because of those small differences in temperature. And those, the lower temperature also means that the snow on the highest elevation side stays about 2 months longer on the ground. So the ground is covered about 2 months more at the highest elevation than the lowest elevation. In terms of the snow disappearance date, which is like, by the date when all the snow has disappeared from the ground, about 30 days. So highest elevation, the snow lasts about 30 days longer than the lowest elevation. In terms of a stream flow, this is the normalized flow. It's a very complicated graph, but I put it there for a reason, because it shows that even though we have the same amount of precipitation, you see that the stream flow is not only varying in the time, but on any given year, you see a lot of variability from one catchment to another catchment, despite having the same amount of precipitation. And that's because, it matters in terms of stream flow, whether it's the precipitation falls as rain or snow, and then what kind of vegetation you have, how dense the vegetation is, what kind of soil it is, and how deep the soil is. So all those factors create about the same level of variability in a space as you have in the time. If you normalize that stream flow by the precipitation, what we call the runoff ratio, which is like how much water you get out of a catchment for a given precipitation, what you see here is, except few years, the numbers are less than 50%. What it means is that, you know, the evapotranspiration dominates the, you know, the hydrologic, you know, the evapotranspiration is the dominant flux in this catchment, okay? And what you also see here, this line that shows kind of, you know, shows the downward slope. That means that the high elevation, you know, the Bull catchment and low elevation Providence catchment, they're converging in the same direction because of the recent, you know, the dry years. So the recent dry years are making the two catchment very similar. If you take the average discharge and plot it as a function of elevation, what you see here is about 50 millimeter increase in discharge per 100 meter elevation gain. So stream flow increases by 50 millimeter per 100 meter elevation, despite having the same amount of precipitation. And the reason is because, you know, if you look at the evapotranspiration, that declines about the same magnitude. So 43 millimeter decline in evapotranspiration, so that excess water that the trees are not using is available for stream flow. In this graphics, what I'm showing here is that, you know, that evapotranspiration, that's the water that trees are using, is less variable from one year to another year compared to the precipitation as well as the discharge. And what it means is basically the trees, they have the first hand on the water. So whatever water that rains, the tree they get to use first, and then whatever is left, that's available for the stream flow and things like that. Here is another matrix that shows that the drought sensitivity, or the like how sensitive those catchments are in terms of drought. And this is the, you know, the 5 bars that shows the high elevation Bull catchment, and this is the, you know, the low elevation Providence catchment. And what you see here is the Bull catchments, you know, they are less, you know, susceptible to drought, even though they have a shallow soil. And the reason is because they don't have as much dense vegetation there. So the vegetation is not as dense as the Providence. So the vegetation is using less water. And also the snowpack lasts about 30 days longer. So that means that there's a carryover from one year to another year. So whatever is leftover moisture in the soil, that goes from one year to another year. So even though if you have less precipitation on a given year, that carryover storage, you know, fills in for some of the deficit. So just to summarize, so we find no increase in precipitation over this, you know, elevation band. And main driver is the temperature and how the temperature plays out in terms of the snowpack. We find that the stream flow, even though the precipitation is same, the stream flow increases by about 50 millimeter per 100 meter elevation. And that's about, you know, same as the decline in evapotranspiration. We find that the spatial variability in the stream flow is quite significant, even though those catchments are kind of, you know, grouped together. And we also find that the high elevation catchments are less susceptible to drought than the lower elevation catchment, mainly because they have less dense vegetation, more precipitation falling as snow. And that, you know, the two things, you know, acting as a kind of drought, acting in terms of drought resistance or drought buffer. I think with that, I will take any questions if you have. Thanks.